I am truly pleased to introduce his Millikan lecture on the make-believe world of real-world physics.
Thank you. Beautiful. Thank you.
I don't know, is he there?
Yes, it's right there. Thank you, Harvey.
Okay, you're welcome. And then I have to, one more thing.
Thank you very much. Thank you. Thank you.
Have a good talk.
Thank you. Dear Professor, I still don't believe heavy and light things fall at the same speed. A feather and a stone, for example. You kept saying I'd get it if I lived in a vacuum. Do you live in a vacuum? When I read this poem by Nin Andrews, which is basically a collection of emails sent by students to her husband, James Andrews, who teaches physics in Boulder, Colorado, I was reminded of something that happened early in my own career. Many of you know these anecdotes, but I'll repeat it anyway. When I started administering the force concept inventory to my students at Harvard, something truly shocking happened. A few minutes after giving this test for the first time, one student got up and walked up to me and said, "Professor Mazur, how should I answer these questions? According to what you taught me, or according to the way I usually think about these things?" Well, ever since that day, I have been wondering what it is that makes students who've taken some course, some introductory physics course, not physics majors, but other non-physics majors, wonder why there's this, I've been wondering why there's this difference between the world of physics and the real world. So in preparation for this lecture, I decided to go around Harvard Square and interview people who were screened for not having taken any physics courses and ask them whether they thought physics applied to everyday life. From what you know about physics, do you think physics applies to the real world?
Yes.
Yeah, I'd say so, definitely.
Sort of. Like, yeah, I'm not sure. I think some basic knowledge, but I don't think you think about it every day.
Good question. I'm sure in some way it does. Okay, for me personally, I find that it's almost on a totally different plane of existence.
I'm sure it does, but I don't really know how.
Well, it sort of kind of governs it, doesn't it, in a lot of ways? I mean, physics describes how the real world operates, the material world.
That's what we physicists like to hear, yes.
Yeah, it does.
In what way?
I don't know, things like gravity and that sort of thing apply to everyday life.
I'm sure it does.
Yeah, definitely.
Definitely.
I just don't know if it applies to what I do every day.
So, you know, if you were to poll the audience here, I'm sure you would get a resounding yes, right? Because, I mean, why otherwise do physics? Physics is the science of the real world. This little exercise taught me that if you ask this question to people who've never had any physics, I mean, you get some hesitation, but it's generally very positive. However, when you take students who've taken an intro physics course, non-physics majors, instead of moving them closer to the point of view of a physicist, we move them the other way, and there are serious doubts about the connection between the real world and the world of physics. This talk is aimed at answering the question, why? Why are we moving the students the wrong way? And the message, in case you doze off, but I promise you I'll do my best not to let you doze off, is that we need to be more careful about the way we represent physics. To make my point, I'm going to ask for a little bit of introspection. And that is really hard because it's much easier to criticize others than to criticize yourself. So I'm going to ask you to sort of leave your own perspective as a physicist and to occasionally put yourself in the shoes of a non-physicist. Somebody is either just about to enroll in a physics course or has already enrolled. Well, like all my talks, I've divided this talk into 3 parts, or 3 movements, as Harvey Leff just said. The first one is to illustrate that because of what we do in our teaching of physics, we paint a world that is really weird and really different. And to make it even worse, truly confusing. So let me start with the first part, the weird world of physics. You've just enrolled, you've gone to the bookstore, plunked down $150 to buy one of these tomes, and you bring it home, and you open the book, and it doesn't take very long for you to realize that physicists are really, really strange people with very strange table manners, for example. And that the physicist's conception of tables, and especially the size of tables, is very weird too. This table, for example, allows you to literally crawl from the USA to Europe. And look at that apple, which is about the size of France. Maybe these are the apples that keep a doctor away. Also, physicists' leisure time activities are kind of amazing. I mean, this is a favorite, a slingshot into a bear's mouth. And when physicists are at the beach, they like to use a slingshot to throw stones at a sunbather lying across a fence. Fields bring really great thrills to physicists. For example, here is a physicist tightrope walking on an electric field between 2 capacitor plates. Now, fields also govern the interaction between physicists of the opposite sex. For example, here is an example of the courtship between Bill and Sharon. And as you can see, Sharon carries a charge past Bill, who then exudes some sort of magnetic field, and you may think that's a bad idea because then you start moving in a circle, but no, it's really a devilish plan because there's dissipation, and Sharon will run out of energy, and as her speed turns down, she'll spiral inwards and collapse ultimately on top of Bill. Now, going to the cosmic scale, we have this very interesting game called the moon wrench game. And the purpose of this game is to use a really long wrench to exert a torque on the Earth equal to the torque exerted by the moon on the Earth. And the text specifies then you can assume that you can brace your feet against the solid firmament, which is illustrated there at the bottom, as you can see. Now, when you get tired of this game, given that we're in space anyway, there's another favorite activity, the so-called cream pie astronaut game. It's a bit messy, so you may need to clean up afterwards, but you do that very simply by surfing. Now, physicists are not known to be really good surfers, so you have to have a special type of surfboard, as you can see here. And when we're all cleaned up, we're ready for the absolute ultimate game, pulling a train by your teeth. I wish I was making this up. I am not. Physicists also have very interesting fascinations. For example, look at this one here. This deals with the convection of air up robes. See these animals there on the side? Physics textbooks are veritable zoos. Check out, for example, this penguin here that's looking underwater using a periscope. And the primate section of this zoo is very heavily inspired by the Reverend George Atwood. Plenty of examples of monkeys pulling themselves up on pulleys. If it's not a pulley, then of course it has to be specified that this is a completely frictionless tree. Have you ever seen a frictionless tree? And when there are no bananas, you use a mirror. I've already mentioned, or not, I've not mentioned, but I've shown a spherical cow. Familiar animals often take on very peculiar forms. There's not just spherical cows, there's also the tubular segmented cat. Now, there are no such things in any other disciplines. I think this silly art just makes us look really, really weird. You look in a biology book, look in a chemistry book. I've looked in numerous examples and been unable to find similar types of examples. The problem, however, is much, much deeper than this. I've just scratched the surface here. And now that we've got these first impressions out of the way, let's delve a little bit deeper. And the example I'm going to use is one of parabolic motion. I mean, we heard a couple of people say that they thought physics applied to gravity and motion. What better example is there than to talk about parabolic motion? And you know, many physicists, psychologists have studied parabolic motion. This is an example of a paper called Intuitive Physics by Michael McCloskey, which appeared in the Scientific American in 1983, where he's at Johns Hopkins University, where he discusses the conflict between the Newtonian notion of motion and the intuitively held beliefs by people. And this is one of the illustrations of this article, and one of the questions is which of those three paths shown most closely resembles the path actually taken by the ball. Now, before I show you what lay people and other people have to say, I'd like to see what this audience thinks is the correct answer. You know, there's no credit or anything, so don't worry. I don't have clickers, so we're going to use a very low-level technology. At the count of 3, you're all going to show either 1, 2, or 3 fingers for A, B, C. And if you don't, then I'll pick on you and you have to stand up and say in front of everybody else what your choice is. So which of those 3 paths most closely resembles the actual path taken by the ball? 1, 2, 3. You've already heard my talk there. 3, 4. There is no 4. So, okay, so I think a unanimous and overwhelming majority for 3. I decided, you know, just to be sure, to go around the Harvard campus and ask my colleagues what they thought was the right path. I've been showing people this illustration, which shows a runner running, and he's represented at 3 different instants. And he releases the ball at this instant, and it has 3 possible trajectories, A, B, C. And I ask people to tell me which of those 3 trajectories comes closest to the actual path taken by the ball. Which one would you pick?
I'd pick C.
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 Provided it was in a vacuum and it was a very messy rock, I would pick C.
Which do I select?
Yeah.
Oh, well, I'd say the parabolic one
C,
going
right.
forward, needless to say.
The person is running.
Running,
I would choose C.
Knowing the answer, or should I sort of
No,
stick to my intuition? Because you know, my intuition still tells me that the B must be the closest to how it works, but I know perfectly well that that's the path C must be the right answer.
Okay, so that's a sample of the many colleagues that I managed to catch on tape at Harvard. Now, which trajectory does the layperson choose? Put yourself for a moment in the position of somebody who's not had physics, and which trajectory do you predict that person will choose? So please, 1, 2, 3. Twos, many 2s. I see a few 1s. No 3s at all. Well, I went around Harvard Square, interviewed 44 people, and I'm not going to show you them at all, but I'm going to show you a few highlights. Which of those 3 paths do you think is closest to the actual path taken by the ball?
B. To my mind, it's B.
I think it's going straight down.
Go with A.
B. Path B.
Path B.
Yes.
Why do you think it's path B?
Gravity. With the weight of the ball, and it's going to go directly down to the ground. I don't see it going any other way.
I think it's A.
I assume B.
This is probably closest.
Trajectory B.
Right.
And what is your reasoning behind that choice?
Things fall down.
I would say C.
Say B.
B.
Why?
I just don't think it would go that far forward if you didn't throw it.
I think B. I think the ball drops directly to the ground.
I'd say that it is, and he exerts no force.
He's not throwing.
He's not throwing, he's just releasing. I'd say that B is the closest.
B is the closest, and what is your reasoning behind that?
If he exerts no additional forward motion, C is too far a trajectory forward to carry the ball, and unless he exerts a force backwards, it wouldn't carry backwards naturally. So I think it would cover, the closest would be B.
So, summarizing, the physicists at Harvard that I interviewed, almost all C, was one who hesitated a little bit between B and C. The person in the street, a pretty wide distribution, peaked on B. So I asked the people in the street that I interviewed who were screened for not having taken any physics course, I have to remind you of that, you know, what kind of explanation they had for this big discrepancy between what physicists say and what they were saying. What would you say if I told you that most physicists, including professors, believe its trajectory is C?
I'd probably take their word for it.
Really? I would have to see it.
I guess I'd just be curious as to why, because it doesn't seem intuitive to me.
I would say, I don't know. I would say it's A.
I would be concerned for the world of physics.
It's like if you threw it, it would do that, I think. But if you dropped it, I think it would drop right there, so I don't know.
What question would you ask them?
Where'd you get that idea?
I would like to have an explanation.
I wouldn't believe you. Well, I mean, I guess I'd believe you because I'm sure you know what you're talking about, but I wouldn't believe them because I wouldn't think that it would be C. If you're not throwing it, then why would it go so far forward?
I wouldn't really know what to make of it. I might trust them more than myself just because they've studied and they have no reason to lie about what they've studied. So I don't know. But I mean, my eyes can't lie. I've seen B, so I'd have to go with B. I'm sorry, I'm sticking to my guns.
To my mind, the ball just falls down.
So what would you ask them about their answer?
If they can give me a proof.
So what did we hear here? We heard the ball can't go that far forward. We heard my eyes can't lie. I've seen B. And then there's one man who said, I'd like to see it. And at the end, give me a proof. Well, we're physicists, so we're experimentalists, so let's do the experiment.
Fire burn, blood around. The children want to have no fun. The children want to have no fun. Fire burn,
Releases it right there. It falls right there. In fact, we should have seen that, right? This is his right foot, left foot, right foot. You can calculate how long it takes to take a full stride and how long it takes to fall from this distance, and you right away find that it's about a quarter. The only way to get the ball to follow trajectory C would be to have the runner run at 25 miles per hour, which is possible because the world record is pretty close to that, but this guy dressed in his long slacks and shirt obviously is not running that fast. Or to turn gravity by a factor 1/4 squared, which is 1/16, which is less than on any of the planets in the solar system. So the answer really is B is closest. Now, you know, the layperson selects a trajectory based on experience, and experience tells the person that the ball falls pretty close from the point where it is released. To us, physicists, it's not the experience that dictates the choice, but it's the model. And of course, the straight down motion that I showed, B, is incorrect because it has to have a parabolic shape. But, and this is the point I really want to make, is that we choose that trajectory even if the representation of that model is wrong. And remember that the last of my colleagues who I interviewed, who said, knowing the answer, or should I stick to my intuition? My intuition still tells me that me must be the closest to how it works, but I know perfectly well that past C must be the right answer, which is the opposite of what my student told me when taking the FCI. Should I answer the questions according to the way I usually think about the things or according to the way you taught me? So the frightening thing is that in our own minds, the model overrides the experience. Now, what do our students see? This was, of course, an illustration out of a Scientific American article. So let's turn to textbooks. Well, here's one example. A woman takes a leisurely stroll, releases a ball, which then very slowly falls to the ground. Do you know what G has to be for this trajectory to be correct? 1/100th the value it is on Earth. Or here, a basketball player who's dropping the ball, and again, he walks like a zombie like this for about 10 steps before the ball finally has reached the ground. This one is a little bit better because sailboats go a little bit faster, so G is actually only 1/5 of what it is here on the Earth. But the problem is that this is part A of a two-part figure, and the other part shows an airplane flying at nearly the speed of sound, dropping bombs which fall straight down. How does this happen? Let's recreate the process whereby this goes from, the author into the textbook. The author makes a sketch, then the art studio, wondering about these strange physicists anyway, dutifully executes. Tens of editors approve. Hundreds of reviewers endorse because they all judge by the model rather than by experience. Thousands of faculty teach from it, and tens of thousands of students grudgingly accept it and then regurgitate on the exam. Now, I think I have to agree with that one person I interviewed in the street that said, physics is almost on a totally different plane of existence. Yeah, I have to admit, maybe it is. Let's look at this illustration again, because it's a particularly interesting case study. Let's remove the trajectory. Very realistic background. We're trying very hard in our discipline to connect physics to the real world. Well, this is the real world. Maybe people don't walk like that with their arms stretched out, but there's no denying that this is the real world. But then let's add the trajectory back. The trajectory, unfortunately, is unreal. So we end up with a realistically rendered background, and on the foreground, an unrealistically rendered physics, which is particularly jarring to the students, I think. Very, very jarring, because there is this attempt to connect to the real world, but the representation completely disconnects it. Now, as some of you know, I've become very interested in visual cognition. 80% of our brains are devoted to the visual processing of information. And I have, in the past 10 years, more than 10 years, been very busy developing a textbook. And one of the things that I wanted to get right was the illustrations and the visual representations. And I think the best way to study how to best represent things is to actually do research. So based on some of these images, I decided to use eye trackers to actually look what people are looking at when they see different types of scientific illustrations. Now, before I do that, I have to tell you a little bit about eye trackers. Eye trackers are two little cameras that look at the pupils of the eyes, and you're sitting in front of a screen with your chin immobilized, and you then see random images. We had a selection of photographs and some scientific illustrations. We didn't tell people beforehand what they were. And then the cameras can tell where the pupil rests. Now, the way we scan any visual scene is by moving our eyes in jerky motions from one fixation point to another. So we move around, then rest our eyes for a few milliseconds before moving it again. The reason is that if our eyes were constantly in motion, everything would be blurred. It's that simple. So what I'm going to show you is, first I'm going to show you a picture that was actually reduced to black and white of a couple of mills that I photographed in Sicily a number of years ago. It shows two windmills near the western tip of Sicily and a couple of salt piles. And you will see a movie that shows the eye tracking motion. So Before this picture came up, the screen was dark, and the person just looked at a random spot, which turns out to be about at 11 o'clock on this diagram. You'll see that as soon as the image comes up, the person moved his or her eyes smack in the center to and this happens completely unconsciously, to the center of the screen to sort of take in the whole scene, and then started scanning the objects of interest. So let's look at that little clip. This is real time. And the circles are the fixation points, so that shows where the eye rested above a certain threshold value of so many milliseconds. I don't remember exactly what it was. So there's a different way of representing it by the duration of the fixation. So the radius of the circle is proportional to the duration of the fixation. The larger the circle, the larger the person looked at it. What did the person look at? The two windmills and the two salt piles, because there's not much else to see. And the salt piles were looked at longer because it's not readily identifiable. So what happens now when you show people realistic renderings of physical phenomena? And the first example I want to show is an illustration that I made for my manuscript, which just shows an experiment that you all know, where you shove a cart down a track, it fires a ball up and lands back into the track. So where do people look at? At the parabolic motion and at the cart, because there's not that much else to look at. So what about some current textbooks that teach parabolic motion? Here's a diagram, and there's a caption that explains what the situation is. Two hikers are lost in a mountain, and a plane comes to drop a rescue package. What do you think people look at in a diagram like this? People look at people, exactly right. The way we decide what to look at is pre-programmed biologically by millions of years of evolution. We don't even control it. The reason people advertising agencies put people in advertising for products that have nothing to do with people is simply because they know that we'll stop on that page and look at the person. So people, and what else? No, airplanes, we didn't evolve with airplanes. But there's something else. Text is a magnet for the eye. So the 100 meters, the X, the Y, the 40 meters per second, simply because reading takes a significant amount of time, of visual processing time. So text labels and people, are they potential enemies? Are they potential mates? I mean, you have to scan them. What about the trajectory? Here's another diagram. I find this a particularly interesting diagram because, you see, this illustrates parabolic motion. Parabolic motion is a perfect example of motion in a plane, and paper is the absolute perfect medium to represent the plane because it is a plane. Yet this is a three-dimensional representation of this two-dimensional motion. So in order to show the reader that this is really a three-dimensional representation of what should be a two-dimensional thing, the artist had to drop a line and another line, it's a complicated thing. So why the three dimensions here? What do people look at? People. And here the trees too, because there might be people hiding behind the trees. And again, the text label, and interestingly, the ball here in mid-flight. You see that? Here's another one, and oh boy, look at that. People running around and the horizon with trees. You've got to scan this all. And here, all these text labels that draw the eyes away. So people look at people, at text label, at other distracting elements, but not at a parabolic motion. So I think that two things are important to retain from this middle movement of my talk. One is that incorrect representations disconnect, like for example the parabola C, to the beginning learner, disconnect physics from reality. And that realistic rendering of backgrounds actually are a distraction rather than a help, and do not do any good in tying physics to the real world. Well, this brings me to the final part of my talk, where I'd like to move from visual representation to verbal and symbolic representations. What is the first topic that we encounter in most physics textbooks? It's vectors. And as we all know, students are confused about vectors. Why? The question I'd like to pose is, suppose you take a vector and you decompose it into two components. Are those components vectors, yes or no? So let's have a quick poll here. 1, yes. 2, no. I'd like to see a show of hands now. Yeah, 2s, some 1s. Ooh, some 1s and a halves. So we're not unanimous about that. So let's look at a textbook. Early on in the book, vectors get introduced, and in this example from a current textbook, on page 18, there's the first illustration that shows a vector A that's being decomposed in two components, AY and AX, and as you can see, they're both vectors. Turn the page to page 19. All of a sudden, the components are scalars, signed scalars. Turn the page again, 20, there are no diagrams. 21, again, scalars. I think I figured it out. On even pages, components are vectors. On odd pages, they're not. Oh, wait a minute. On page 23, we have a problem because the components are vectors once again. What about forces? Well, forces get introduced on page 121, and there's the first decomposition. But this is an odd page, but forces are vector on odd pages. Turn the page. Oh no, all of a sudden they've lost their vector sign and they're no longer vectors. I can imagine students saying, I don't understand vectors. And the problem is that we know what is meant, and therefore it's very hard to catch these things. So let's go from representing vectors to working with vectors. Here's a little passage which is out of a current edition, and I want to highlight one sentence in particular. This is talking about buoyancy, so there's a block that is submerged in liquid, held up by a scale, and you see the free body diagrams on the right. Let me blow this up a little bit so that you can read it. The difference in magnitude of these two forces, F1 and F2, is the buoyant force B. Sounds good? Several problems here. I've shown it to a lot of people at Harvard, and people look at me and think that I'm from outer space because it looks good. It's all is fine. But you should be able to identify at least two problems with that statement. One, it should be a plus, but that's the hardest one. I have very few people identify that. It should not be F1 minus F2, but F1 plus F2. That's one problem. What's the other problem? Magnitudes. It's not the magnitudes, it's the vectors. And you know, I used to be completely unaware. This, by the way, is not the first edition of some book. It's the 5th edition. You know, and I used to be completely unaware of it. And I think that the problem is that once you know what is meant, it is very difficult to pinpoint the difficulty. It's the same sort of like the difference between the spoken language and the written language, right? When you speak, you can omit a word, you can misspeak, but people still know what is meant from the context. A beginning learner in physics has no context. And then these inaccuracies become major stumbling blocks. And the real difficulty is that it is so hard for us, and I'm no different from you, to find these things because we just read straight over it thinking, you know, we understand it, it's right, it's correct. And this was rubbed very strongly under my nose when I started class testing my own manuscript about 10 years ago. I have to tell you a little bit about what I have been doing. I've been writing a textbook where I've been developing physics starting from the conservation principles rather than the laws of motion from Newton. I mean, in most of physics, the laws of Newton are, the concept of force does not appear, yet the conservation principles survive in all parts of physics, from nuclear physics to you name it, it's everywhere. So, and there's certain aesthetic appeal at knowing that the universe is governed by conservation principles and by symmetries. Plus, a third advantage is that conservation principles is simple algebra. There's no calculus. F equals ma is a differential equation, but you know that something remains constant, or that something before is equal to something after. That you know, is just algebra. And in fact, in most physics books, what we do is we have people go through mechanics, and solve complicated problems. And then we do conservation principle, and we show that you can do those same problems in just 2 lines. Why not start with that then? Anyway, so I wrote my first chapter on conservation of momentum, and I was pretty proud of that, following the approach of Ernst Mach, and based on experiments using ordinary cards. And you know, I gave it to my students to read, and I've used for 10 years just-in-time teaching and the feedback from just-in-time teaching to analyze my own writing. I've asked students, you know, to tell me what they found difficult or confusing. 10 years in a row, 200 students, twice a week. It's a phenomenal tool for fine-tuning your own writing. And when I gave this chapter on conservation of momentum, where the most complicated equation is P1 before plus P2 before equals P1 after plus P2 after, students said that they were totally confused. Let me give you an example. Consider, for example, this collision on a low-friction track. Card A comes in and hits B from the back. And statements that were in my chapter, these are a certain number of statements that were grabbed out of my text. The momentum of card B is not conserved. Momentum is conserved. The total momentum of, these were not right after one another. I write better than that. These are just a few sentences, you know. The total momentum of the cards is constant. The momentum of cards A and B is conserved. You know, to us, these statements all make sense. But you know, my students were totally confused. I thought they were going to say nothing was unclear, but no, they were all confused. Here are some typical remarks that my students made. I'm confused about conservation of momentum. Why is momentum not conserved in a non-isolated system? Is momentum conserved in an inelastic collision? I'm confused as to how and when to apply conservation of momentum. Now, let's think about conservation for a moment. It involves many different concepts. For example, it involves the concept of system, which is probably, I think, one of the most basic concepts in physics. Yet we rarely ever spend any time discussing it. System is just a system, collection of objects you discuss, but it's really much more profound than that. And the system, the quantities that are of importance when discussing systems all need to be extensive quantities. I never realized how important the concept of extensive versus intensive was until I realized student difficulties here. It involves things like destruction and creation, interaction, and whether or not things are constant, meaning no change over time. So let me ask the question, what is the simplest way to express the conservation of a quantity, an extensive quantity, it has to be extensive, Q? One suggestion is delta Q equals 0. I would like to have a more deeper one. Well, I hear a lot of, I would say, you know, the most basic way, the most simple way, which is not mathematical at all, is that there cannot be any creation or destruction of this quantity Q. Take energy, for example. You cannot destroy energy. You can convert it from one form to another. You can transfer it from one object to another. You can move it from one place to the other, but the total amount of energy is constant. That is what embodies conservation of energy. In other words, there is no destruction or creation of this quantity in the universe. Of course, we rarely deal with the universe as a whole. We usually deal with a system. So let's consider a system. How can the amount of quantity Q, let's take an extensive quantity, the number of people inside this room would be a perfect example. How can it change? Well, it can change because of input and output. People coming into the classroom, the theater, and people going out. Is that the only way that the number of, I should have said living people can change? No. Somebody could pass out or give birth, and that would, of course, change the number of people in this theater too. I hope neither of the two will happen during my talk. Now, how do we express that mathematically? Mathematically, we say delta Q, the change in this quantity Q, is equal to a flow into this system right? And the flow is positive when it's in, negative when it's out. And it's equal to a source term, S, which accounts for creation or destruction. Now, if the quantity is conserved, there's no creation or destruction, and therefore SQ is 0. So in a sense, writing down delta Q equals the flow is the essence of conservation, because it already assumes that there is no source term. Don't worry, this is not the way I explained it in the textbook. I mean, but you know, I trust you can follow what I'm saying. Now, if in addition to being conserved, meaning there is no source term, the system is isolated, then Q cannot change. So the statement delta Q equals 0, which I heard a number of you say, has two conditions. One, Q is conserved. Two, the system is isolated. If we lock all these rooms up here, all these doors, and there's nobody going to leave or enter, the delta Q, where Q is the number of living persons in here, is going to change. I trust you. We're not going to try it, but it's going to change eventually. So delta Q equals 0 in that case is not embodying conservation of the number of living people in this theater. So conservation plus isolation means constant, but conservation by itself does not mean constant. Here's what I told my student. I told my students conservation laws, are the most basic principles of physics. One example of a conserved quantity is momentum. Then I showed them collisions, and I, made several statements, and then I say the momentum of card B is not conserved. Wrong. What should that statement be? The momentum of card, and I can imagine students then saying, this is not from that book, by the way, if conservation is so fundamental, then why is momentum conserved only in certain cases? What I should have said instead is conservation laws are the most basic principles, momentum is conserved, the momentum of card B is not constant because it doesn't constitute an isolated system, and some momentum is transferred to it from card A. So a conserved quantity is always conserved. It's constant, not conserved for isolated system, and can only change due to transfer across the boundary. It's not just me, by the way. Oh, so let's first look at those four statements. What about that first statement? I've already told you that's wrong. That should be the momentum of card B is not constant. What about the second statement? Fine, right. What about the third statement? Fine, too. What about the last statement? That too, I mean, of course, it's sort of ambiguous, but it's a misleading statement because it seems to imply that in some conditions the momentum of cards A and B cannot be conserved. What should be said is because it's an isolated system, it is constant. So I became aware that there's a big difference between the words constant and conserved. And it's really not just me. I mean, here's a concept at the glance box out of another textbook, and somewhere in the middle there's this decision point. Is the sum of external forces equal to 0? Yes, momentum is conserved. No, momentum is not conserved. I can imagine that that can be very confusing, and I think the lack of precision in our language. See, the problem is, again, we know what is meant. Whether we use the word constant or conserved, we know exactly what is meant, and the mathematics will work out because we know what is meant. But to somebody who doesn't yet understand these concepts, that lack of precision can be really, really confusing, and it's not easy to find out about it because we're ourselves so insensitive to it. So I believe that we can synthesize the three parts of my talk by saying that we really need to be more careful with our own representation. And as I've already said a few times, but I think I'm going to emphasize because that's really the take-home point of my talk, it's not going to be easy. It's not going to be easy for two reasons. One is it's not going to be easy because we're unaware of it. It's very hard from our own perspective to see these things. And I think the other reason is best illustrated by another poem by Nin Andrews. Dear Professor, you keep saying that science is all about proof. If you prove that what we believe is wrong, We should change our minds. But minds don't change like that. We keep proving it every time we take another test. It's not just students' minds that are hard to change. Our minds, our own minds, mine included, are just as hard to change. Let me show you how my colleagues reacted when I told them that choice B was correct. What would you say if I told you that I actually think that the people are right?
Right in what sense?
I'd be surprised.
Well, I would, my reaction, my internal reaction before I vocalize my answer would be to say, I wonder which limit he's talking about.
The non-physicist is right. In what sense? You mean that the ball drops straight down?
With respect to the person that's...
No.
Well, I'm sure there's some sophisticated sense in which you're going to explain it to me.
Oh, I'd say you've got a problem.
So, we've got a problem. But I think that being aware of the problem is halfway to having solved it. Now, many people have contributed to the development of this talk, so let me end by acknowledging all of their contributions. Thank you for your attention.
Wonderful. Excellent. You want to take some questions? We have a few minutes.
Thank you.
I agree, that was wonderful. Eric said that he would take some questions, and we do have a few minutes. Let's see, are there microphones around? There had been one over here. Well, there's a question, I think. Yeah, could you put up the house lights, please? Thanks.
A simple question, excuse me. Did any of the physics people, when they first saw the models of projectile motion, say that seems over-exaggerated, or did they just say the projectile or the parabolic motion is correct and I'm going with that baby?
The only hesitation is the one I showed you where my colleague Masahiro Mori asked, what did he say exactly? I forgot his words, but my intuition tells me that B is the closest, but it must be C. That was the only hesitation. The others was C, right? They were even offended that I asked them that question.
Would you be willing to identify the simplest concept in your textbook?
The simplest? Wow, that's an unexpected question. I don't know. I'm sorry, but I have to think about that. I think no concept is simple. I mean, sometimes I'm surprised at how we manage to learn. One of the things I've always been telling, up to this very day, I've not talked about my textbook. I've only talked about peer instruction, about my approach to teaching. And I've always said in my talk about peer instruction that the person who learns the most is the person who's teaching. And this interactive teaching puts the students in the role of the teaching. I've discovered that the person who really learns the most is the person who writes the textbook. because it makes you examine things, you know, really at a very fundamental level, and it gives you much more time, of course, to ponder the different things. And I don't think there are any simple concepts. No wonder, I mean, we've taken thousands of years to develop our discipline.
Thank you. It was a very interesting talk, and I loved the illustrations. I think Aaron said something to the effect that even if we think lecture's not very effective, we should still, you know, that doesn't mean we should be unclear when lecturing. We should strive for clarity. But I was wondering if you have any evidence that these more clear explanations were more effective for the students in terms of their understanding. For instance, you know, the difference between constant and conserved. Was that something which they appreciated, or was that too nuanced for them to grasp?
Well, students never appreciate anything. But we have very carefully tested their performance, and even though, you know, a manuscript has been under development, there's been a clear jump in a number of metrics that we have, and I'll be glad to show you this data at some point. Now, the reason I made that initial remark about students not appreciating anything is something that I actually at some point would like to talk about much more, and it's that I've noticed that as you attempt to explain things better, or to accomplish more what I'll call learning, either in the classroom by changing your approach to teaching, or in the textbook by trying to improve your writing, you end up soliciting not fewer questions, but more questions, right? And that makes sense, because how do we learn something? We learn something by wondering about something. And if you take a very surface approach to learning and reading and so on, you're not going to end up with many questions. So as you try to suck the student more into, you know, engaging into her or him into your teaching, or the reader into your writing, you find that there are more questions. And it's very easy to misinterpret that reaction as your approach being more confusing than anything else. So I think we all have to be prepared that as we try to improve our approach to teaching, we are going to get more questions, not fewer. And that is a good sign, not a bad sign. But I think it's easy to misinterpret that as a bad sign.
Okay, I was wondering, your projectile motion survey, if you surveyed professors from other departments like engineering, chemistry, and biology, and would their answers fall closer to the lay people or to the physicists?
No, I haven't. I mean, I showed you most of the people I interviewed, not all of them, but most of them, and they were all physicists, including Nobel laureate, as you probably saw. But no, I haven't done that. It would be interesting to do that.
I noticed you dealt with spherical cows. Did you deal with any sacred cows? Any that you decided to drop?
The sacred cow is the subject of this talk.
So was there any content that you were willing to drop out of a textbook that you tried to get published?
Oh, I'd be willing to drop a lot of content, but that's not the question. The question is, what content are you willing to drop? The adopter. I'm sorry, I'm willing to drop a lot of content. In fact, I have dropped a lot of content in my own teaching. Charlie.
Well, I wondered, what was the reaction of your colleagues to your explanation? We saw them doubting.
So let me repeat the question. Charlie Holbrow is asking me what the reaction of my colleagues was to my explanation. And it's difficult. I mean, first of all, they were on camera and they had signed a release. But secondly, you know, it's just hard to admit that you were wrong. To get back to peer instruction, which is one of the reasons I'm here, I've tried demonstrating peer instruction with faculty. It works beautifully with students, but I've done it with faculty. A number of years ago, Joe Reddish organized a meeting, 10 years ago, when was it? At what? 96, 12 years ago, time flies, at the University of Maryland, and he asked me to teach a demonstration class, and there were about 140 people, including most leading textbook authors, and I asked a question about a subject I knew most physicists skimmed over, fluid statics, and about sinking and floating, and I knew it was going to challenge them. And I asked a question, 40% got it right, 60% got it wrong. I asked them to turn to each other to try to convince one another of the answer. Fist fights broke out. This was about 1.5 hours into a 2-hour lecture. I needed a glass of water. I walked out to the bathroom to get a glass of water. Nobody even noticed that I walked out. I came back. I got them to listen to me again, and I said, please, vote again. Nobody changed their mind.
Yes. All right, let's thank Eric one more time.